So while I'm trying to get them sorted, you can look over that and try to make it make sense in your brain. Archie, are you here? Archie. No, I don't see Archie. Okay. All right, I gotta keep an eye on that. Okay, sorry about that. Are there questions on this one? Again, I know this topic is, it's not an easy thing to grasp right away. Like, don't feel bad if you're kind of struggling a little bit. Struggle is how these go, unfortunately. Okay. And one more thing, I'm sorry. Okay, let's look at the next one then. So, well, first off, so compare doing this with the truth table. Which one seems cleaner? This proof does. I know once you forget about all the scratch work you had to do off the side. Now some of you might say, well, I like the truth table better. Yeah, sometimes you do. But we got to get used to kind of both ways here. So as I've kind of already said, sometimes you don't necessarily see the next step in the proof that you need to use. Sometimes you're going to have to kind of go this back and forth kind of deal of kind of seeing where you want to go and seeing if you can work backwards. Sorry, just seeing things in chat. About the steps in WebAssign, we're asked for a math expression. So, well, they were asking for if WebAssign has an option for like breaking down the problem into steps. The answer to that was no. In terms of writing math expressions for those essay questions, I thought it pulled up a like mathematical like toolbar, if you will. Oh, these ones. Yeah. So those ones in the, sorry, I was misunderstanding. What you're going to do there is you're going to, what it wants in that column is essentially these numbers here. Like what line did those steps use? So like that first one, line 3, De Morgan was used from step 2. So you would want 2 in that steps thing. Mathway is terrible. Never use Mathway. It's horrid. Anyway, I'm salty about Mathway. Anyway, this next one. Write a proof for the following assertion. P. So here are the things we know. We know P implies R. We know Q implies not R, and we want not Q. So first thing I'm going to do is I'm going to write down all the givens. I'm just going to start writing for the givens. So we have P. Given. Okay, so now again, I'm kind of going to come off to the side, scroll back up in chat to look at my rules, and try to start figuring out things I might be able to use. So I want not Q. So let's go back again and try to figure out some of these rules that could give us not Q. Well, again, if I look at those implication rules, the inference rules, have I been saying implication? The inference rules. Again, if I use the one that ends with not P, that might work. So that one's going to be modest tollens again. Modest tollens and modest ponens are kind of like your best friends. So if we want not Q from modest tollens, what we would need is we would need Q implies something. So either P or R in that case. So let me put a question mark. And then we would need not whatever that thing was. Well, specifically because I have Q implies not R, let me go ahead and change that question mark to not R, because that's actually something that I have. So that is most likely something that I could actually potentially use. So if I put not R there, I have to put not R here as well. So that's an option. Both of those not R's could be P's, but I don't have Q implies P in any way. So for right now, I'm going to hold off on that. Well, what are some other things that could get us not Q? Well, I could go with ponens again. So modus ponens, but I was lazy and didn't write modus. So if we wanted not Q here, what we would need is we would need something, and something implies not Q. Okay. Now, we don't have not Q either. We don't have anything implying not Q. Maybe we could potentially manipulate step 3 to get there, but let's just leave that question mark to remind us that that could be either letter that we want it to be. But that one seems less likely. Modus tollens, since I have that Q implies not R, that one seems like a pretty decent way to potentially start going. And here's the other thing about proofs. Sometimes you might start in one direction and get to a certain spot and then realize you can't go any farther, and then you have to go a different route from the start. So again, these things take time and practice. Sometimes you start going down one road and it doesn't get you anywhere, and you realize that there was another road you should have went down on. So let's go ahead and focus on this modus tollens one, because that one seems like it might work because it at least has something that I already have. So now I would try to say, well, the thing I don't have is not R. So is there somehow that I could have not R? So the thing I want now is not R. Okay. So now let's start thinking of ways I could have not R. Well, if I had just plain old R, I could get there with double negation. So if I can have plain old R, that'll get me there. Well, can I figure out, is there a way that I can get myself R? Well, then I go and I look at my rules and I say, okay, well, what could get me R? Both of the modus ones are looking good ideas again. So I know I might sound a little weird as I'm going through this, but I'm actually trying to talk as if I was talking myself through this proof myself. Like, yes, I could just give you the answers, but I'm trying to talk it through as if I was actually doing this on my own. So I'd go back to my rules and I'd say both of those modus ones are looking pretty good because I have some implications. And let's see, specifically that modus ponens one is looking really nice to me right now. Because with modus ponens, well, that says if I have P and P implies R, that would get me R. So again, sometimes you have to be really creative and you got to change in variables to different, the ones that you actually have. So, well, that's awesome because that gets me the R that I could then double negate to get not R, and then I could use modus tollens to finish. Well, whoop-de-frickin-do! I have those two things that I needed. So essentially, I personally almost find working backwards better. Working backwards doesn't always work either. So the other thing you can do is you can go forwards, and sometimes you can say, okay, well, what do I have? So now I was working backwards this entire time, but let me kind of shift really quick and come over here and say I hadn't thought about any of that yet. And I know you're like, well, it's already in my head. Well, pretend it didn't happen. And say I was looking at this with fresh eyes and I was saying, okay, I'm going to look at what I'm given and I'm going to figure out things that I can find out. And I'm just going to start writing stuff down. One thing that I could find is if I use that would get me R. And say I didn't know that I needed that yet. And I keep looking and looking and I say, well, if I use modus ponens, so say I held this 4 and made it a new statement. If I used modus ponens on 3 and 4, I could get not R. Well, that's cool. I could get that for some reason. and say I named this 5 just so that I can refer back to it later. And then one more. And then if I used double negation on 3, I could get not Q implies not R. Maybe that helps, maybe it doesn't. And I'm going to stop there. But you could essentially just keep looking at things that you could pull from the givens. And sometimes you're going to do a little bit of this and a little bit of this other stuff over here. And you're going to kind of go both ways and try to meet in the middle. So I know I'm saying a lot. So we already had the answer pulled out before I did all this hoopla over here. But the hoopla over there that I just did, I just wanted to show sometimes you can take what you're given and just mess around with some rules and just say, well, I could get this, I could get this, I could get this. Don't even give a care if it's helpful or not. I'm just going to start listing off some things and then see if I can somehow piece it together. Okay, so like I don't need this not R. I don't need this not Q implies not R, but I could have them if I had needed them. So I just started listing off some things that I looked at the rules and said, you know what, these givens could give me this if I wanted to. And try not to go too crazy on the double negation because, yes, you can always double negate anything you freaking want. So just be careful with that one. So anyway, we already had what we wanted, so let's put it together. So let's remind ourselves what we wanted and what steps we're going to be using to get there, because now I've got a lot of stuff floating around everywhere, and it's all kind of squishing together. So I got to remind myself that I definitely went with this modus tollens, but then I wanted that not R. Well, I got that by finding regular R and then double negating it. Okay, so that was the backwards way, so now we got to go the reverse for my actual proof. So the first thing I needed to get was the regular R. Well, that came from modus ponens on 1 and 2, which again, if you had gone, you know, the front way first, if you will allow me to say it like that, the front way, you might have also realized that you could get that from modus ponens that way as well. So we get R from modus ponens on 1 and 2. And then I can go ahead and double negate it. Which would have, of course, then been on 4. And then again, since I had to work backwards, or since I did work backwards, I know that now this modus tollens rule is going to fall out for me. So if I use modus Sorry, my laptop got very angry. Crap, where did I cut out? 203, that was just about a minute ago. So let's see. So I got R for modus ponens, double. Not R, double negation. Cut out before you explained 6. Okay. So 6, again, so once I had that not R, I go back to the space where I was working backwards and say, okay, well, I needed that not R for this modus tollens rule. So then the next step was that I used the modus tollens to get me the not Q that I wanted. So not Q came from the modus tollens on 3 and 5. And not Q is what I wanted, so I'm done. So with this proof, again, with proofs in general, you're not just going to be able to write it out straight away. You got to kind of go off to the side, do a bunch of hoopla, and figure out how the puzzle pieces fit together. Sometimes you can go forward, you know, kind of a forward direction, say, what are my givens? Look at my rules. What rules can I use to get me things? I don't even care if I need them or not. Let me just start listing some things that I can get. And sometimes you're going to want to go backwards. So maybe those arrows are in the wrong direction, but sometimes you're going to want to go backwards, and you're going to want to start with what you want and look at the rules and say, okay, well, what can get me what I want? And then kind of work backwards. And sometimes you can find ways to meet in the middle. And then you've just got to kind of take a step back and say, okay, I have all the pieces. I also have some pieces that I don't need, but I have all the pieces. Now I just have to put them in the right order. Hopefully that made sense. So I know I babbled through that one, but again, it was babbling because that's exactly how I would talk myself through it if I was doing this on my own. I'd say, okay, what do I have? How can I get there? What do I have? What can I get from that? What do I need? How do I get there? And kind of just meet in the middle. If there are no immediate questions on that, again, we kind of got to move on. So again, I will put up more practice on WebAssign for anyone who wants to try them. I will write out the full answers and post them on Blackboard when I get a chance. But again, with the quizzes and exams, it is much more focused on just listing the rules and the steps. So the rules and the numbers of the steps that you're using, than actually doing these fully out completely from scratch. Okay, so you're feeling good about the inferences, but the equivalences are hard. It's kind of nice with the equivalences because it's literally just, I can replace this with this other thing. So I will say that the inferences come into play usually more often than the equivalence rules. Like modus tollens and modus ponens, again, are usually your best friends. They come in a ton. And I know in that number 25 that I started it off with, didn't use it at all. But modus tollens and modus ponens are used a ton. So you're going to want to get very comfortable with those, very comfortable with changing them to the different, you know, variable names, if you will, that you're working with. But again, unfortunately, we got to move on because we already way behind. But it's all right. So I've got to move on to 1-3. So we're going to start that now once this decides to work. And I've got to unshare my screen and reshare the right one. So give me 1 second. So 1-3 is already up on Blackboard. I think it's been on Blackboard for a couple of days because we were supposed to get there already, but it's all right. Okay. So 1-3 is this thing called predicate logic. So we had formal logic, and then we just went through propositional logic, and now we have predicate logic. So all the logics. So previously, back in 1-1, which feels like 5 years ago, we said that something like x is even was not a statement because x was free, and since it was quote unquote free and could be anything, we can't say whether it's true or false. But in math, we obviously have phrases like that a lot that have variables in them, so we're going to have to figure out a way to actually be able to use those, and that's exactly what predicate logic allows us to do. So predicate logic. Blink, blink. So a predicate is a declarative statement whose true, false value depends on one or more variables. So now we're actually going to allow these variables to kind of exist, and we're going to be able to actually look at the true falseness depending on what that variable is. So we're essentially kind of going to use function notation. So function notation is going to be used to denote a predicate. So say, for example, I have the predicate p of x, so that's going to mean that x is even, or q of x comma y, so I can have more than one thing inside there, means that x is faster than y. So as just generic statements, since those are free variables, they wouldn't be considered a statement. But once we add on this little predicate piece where it's going to depend, we're actually going to let this be a value. It's then going to turn it into a statement that's either true or false. So what I mean by that is, whoa, no, stop. I swear. There we go. So say P of X means that X is even. If I have P of 7, well, that would mean 7 is even. Well, that's of course a false statement because 7 is odd. So it's just a way for us to have this statement that depends on this variable, but we still want to be able to figure out whether it's not positive or negative, true or false, but that's just going to depend on what value we give it. Or what if we look at this Q of X comma Y? Well, Q of leopard sloth would mean that leopard is faster than sloth, which would be a true statement. Leopards are faster than sloths. Whereas if I change it around and I have sloth comma leopard, that would be false. I'm not going, well, no, I guess I should be consistent and I'll write it out. Fine. Sloth is faster than leopard. This would be false because sloths are very much not faster than leopard.
Will you?
Yep, go ahead.
Will you please go up for 1 second? My thing cut out. Just for 1 second.
I know, you're good. I'll leave it there for a little bit while I finish talking about this.
Thank you, I got it.
Okay. So here, once we have sloth comma leopard, you know, the order switched. So order really matters here. When you have more than one input, sorry, more than one input, the order definitely matters. So it was the first one is faster than the second one. So we're going to say that the domain is the set of all values that the variables can take. Essentially, just like in general math, the domain is all the things that you're able to put in there. So for example, the domain of P of X above would be all integers, and the domain of that QXY would be the set of all animals. So again, this kind of works exactly just like math. What values are you allowing those variables to take on? We're also going to be able to actually think of equations as declarative statements as well, where we're going to take kind of the equal sign to kind of be the verb, if you will. So here's what I mean by that. So consider the function x squared minus x minus 6 equals 0. We're gonna call that e of x. So that's going to be our, kind of declarative predicate statement here. So we have that the truth of this e of x depends on the value of x. So what if I let it be 4? Well, that would be put 4 into the function. So 4 squared, 4 minus 6. Well, that's 16 minus 4 minus 6. So 12 minus 6, gotta keep track of my arithmetic here, which is 6, which is not 0. So that would be a false statement. E of 4 would be considered false. What if I change it to 3? Well, then if I plug 3 in, I have 3 squared minus 3 minus 6. So 9 minus 3 minus 6, which does give 0. So that would be a true statement. So even though this is just a general equation, since we have it equal to 0, the equal to 0 is kind of the verb in this case. That's the thing that we need to be true or false. And then if we kind of name it this e of x, whatever we plug in is then going to determine whether it's true or false. Okay. So I'll pause in case there's questions really quick, because I know typing things in chat sometimes takes a second. We look good. Okay, moving. So a quantifier is true for all elements of the domain or for just some elements of the domain. So sometimes we're going to want to say this is true for absolutely anything, and then other times we're going to want to say, hey, this is only sometimes true. So we have these two very important types of quantifiers. So we have a universal quantifier and an existential quantifier. The universal quantifier looks like this, an upside down A. And this is going to essentially mean for all or for every. So whenever we see this upside down A, that's going to mean for every single thing we could plug in, the following thing must hold. Whereas the existential quantifier is a backwards E. And this means there exists. Or sometimes you can also say it as there is a. So there is a something such that this thing is true. Now, notation matters. It's an upside down A, not a right side up A. It's a backwards E, not a forwards E. Yes, I will, of course, be uploading these to Blackboard. The blank ones are up there already for 1-3. And the filled out ones will, of course, be there afterwards. So please use the actual correct notation. It's an upside down A and a backwards E. A quantified statement. Is a predicate with a quantifier in front of it. The quantifiers either being this upside down A or the backwards E for all or there exists. So let's see a couple examples of what this kind of does to our logic here. So say our domain is all animals. And we're going to let P of X mean that X can fly, and Q of X means that X has wings. So say I take this statement here, this quantified statement, I would read this as for all X, Q of X implies P of X. Or if Q of X, then P of X, if you prefer. In words, in terms of this specific context, we would say for all animals X, animals. So you always, you always also want to bring in the domain context as well. Whenever you're talking about the variable, you want to refer back to the context of that variable. So this is all animals X, if X, so if Q of X, so if X has wings, then P of X, X can fly. Or if you prefer, all animals with wings can fly, which is a bit more, usual English. But when writing these out, you'll usually go for the logical English, if you will, first. If you want to change over to then more everyday English, you're perfectly welcome to. But notice here, we still have X's floating around, so they're still variables. But this is actually already, sorry, I don't know if you can hear that, my hair is freaking out. Okay, sorry. So even though there's X's floating around still, this statement can actually be determined to be true or false. In this case, this statement is false. Just think of penguins. Poor little penguins have wings, but they can't fly. So because I've tacked on this quantifier, all of a sudden, even though it's still got X's in it, I can still say whether it's true or false. So what if instead I wanted to say in symbols and predicates, there are some animals that have wings and cannot fly. Now going to English, from English to symbols, like almost everything else I've said in this class so far, takes a bit of practice. But essentially what you want to think about here is, so I'm going to write some words first before I get into the symbols. So essentially what you want to think about is this statement is essentially saying, so there is at least one animal with wings that can't fly. Like our poor little penguins. So there's at least one animal with wings, but it also can't fly. So the quantifier we're going to want to use here is actually the there exists quantifier. So there is at least one. So there exists some animal X. So there exists an X such that it has wings, which is q of x, but it can't fly. So it has wings and it can't fly. Has wings and it can't fly. See what I mean? So that first statement, there are some animals that have wings and cannot fly. You might be able to jump from one to the other, but you might also need to remind yourself, okay, if there are some, then there is at least one, there exists one that has wings and cannot fly. Hopefully that makes sense. Got 10 more minutes. All right. So I'll let that set in for just another couple seconds. So I kind of said this already, but since quantifiers change the values of the variable or variables that the predicate can take, the quantified statement, and when I say quantified statement, I mean it either has a for all or there exists. So the quantified statement is either true or false. So even though it's got variables floating around, once we add on those quantifiers, it now can be either true or false, but not both. So this second thing we just wrote, there exists an animal such that it has wings and cannot fly, would be true because penguins. So let me leave that. There we go. Definition: the scope is the part of the formula for which the quantifier refers to. So it's essentially what that quantifier is talking about. So it's going to lie in the parentheses right after the quantifier. So for all x, whatever the heck the scope is. There exists an x, whatever the heck the scope is. Now note, if we had something like there exists an x such that p of x and q of x and r of x, notice that the parentheses after the exists end right there. So the p of x and q of x is in the scope, but that extra and r of x is outside of the scope of the existential quantifier. Okay? If it wanted to be in the scope, it would have to have had, it's a different color, teal. So if I wanted it to be in the scope, I would have had to do, something like that. Maybe without that, this one in the middle, depending on what I was looking at. But so parentheses are going to really matter here with these quantifiers. The parentheses are important. Use them wisely. Okay, I think I can get through this next tiny little bit, and then we will be done for today. So I'll let that get taken down really quick. I'll give it another couple seconds. I guess there wasn't really much to write down in that part, but... And here we go. So again, as I've kind of already said, translating between English and predicate logic sometimes takes some practice. And I know I've said that about essentially every single thing we've gone over so far. So consider the following predicates, where the domain is the set of all mammals. Translate the given sentences into predicate logic. So we're going to have b of x means x is a bear, and f of x means x is fuzzy. Is a fuzzy? No, that should just say is fuzzy. Oops. All bears are fuzzy. Now, we need to be careful here, and this is, again, why it takes some practice. So all bears are fuzzy, which means if it's a bear, it must be fuzzy. Like, there is no bear that is not fuzzy. All bears, if you are a bear, you are fuzzy. Now, you might think that that implies and, but we need to be a little careful because it's actually not going to be and, because that would mean it's a bear and it's fuzzy. But it doesn't quite get the point across that if you're a bear, you must be fuzzy. So whenever you see all, very often the all here should tell you that about the universal quantifier for all x. That is kind of nicely obvious. It says all, it means for all. Whenever you see the universal quantifier all, you are most likely going to be using, when I say most likely, I mean 95% of the time, going to be using an implication. A Okay, so those two kind of pair up, the for all and an implication. So here, when we say all bears are fuzzy, we're going to say for all x, if it's a bear, then it's fuzzy. Because then, no matter what x value you are, if it's a bear, then it's fuzzy. What if I wanted to say some bears are fuzzy? So that means there's at least one bear out there that is fuzzy. Maybe not all bears, but there's at least one out there that's fuzzy. So since there's at least one, we're going to say there exists an x. So there exists some bear that out there in existence that is fuzzy. So there exists an x such that x is a bear. There exists a bear. And that bear is fuzzy. So there exists a bear that is also fuzzy. So here, whenever you have the existential quantifier, this is often going to pair up with and. So again, you kind of get this pairing. It's usually going to happen that if you have an existential, it's going to be an and. So there exists some bear that, I wanted to say there exists some mammal X such that it is a bear and it is fuzzy. So if some bears are fuzzy, that means there exists at least one bear that is fuzzy. So there exists an X such that it's a bear and it's fuzzy. Hopefully that makes sense. Again, it's a little weird at first to go between the English and the predicate logic. But if all bears are fuzzy, then for every single X, if it's a bear, it must have been fuzzy, because that's how you get that all bears are fuzzy. If it's a bear, it must be fuzzy. Some bears are fuzzy. There exists at least one that is a bear and is fuzzy. Not necessarily saying that every single bear is fuzzy, but there at least is one. Now, the nice thing is that these above examples are pretty common setups in predicate logic. So you're going to see a lot of sentences that sound something like all blank are something. All bears are fuzzy. Or something like there is a blank that is something. There is a bear that is fuzzy. Some bears are fuzzy. So maybe, you could also say some as well. Some blank that is something. That doesn't sound like English. Some blank, I guess that would have to turn into R then. I'm going to erase this. So the some bears are fuzzy does get the same point across as there is a bear that is fuzzy. So I'm just going to leave it as that construction. So those are two common constructions, and I kind of already pointed this out. So the first one is going to lend itself, so all blank are something. It's going to turn into for all X, that thing implies the other thing. Where, whoops, those got backwards. My little things got written in backwards. Oh no. So the blank is our P of X and our something is Q of X. So P of X, Q of X. So if it's all P of X are Q of X, it's going to be for all X, P of X implies Q of X. And if it's there is a P of X that is Q of X, we're going to have there exists P of X. And another typo. I was having a ball on typos last night, apparently. This parenthesis in that middle part should not be there. I thought I got rid of that, but I guess not. So if you have there is a P of X that is Q of X, that will turn into the construction there exists P of X and Q of X. So again, the for all kind of pairs up with the implication, and the there exists kind of pairs up with and they're kind of buddies. So I'm going to stop there. And we'll see some more examples of this idea on Thursday. Your next homework set has appeared today because, again, they go Tuesdays to Tuesdays. This next homework set involves 1-3 and 1-4. So we've gotten about halfway through 1-3, and we'll do 1-3, and we're gonna push through the rest of 1-3 and hopefully start 1-4 on Thursday. I might have to reevaluate the homework based off of how much 1-4 we get through, because again we're slowly getting more and more behind where we should be. So we got to start chugging along a little bit. But so your first homework is due tonight, and your next homework is up quiz on Thursday. Quiz on Thursday. Typing in a chat so people can find it later. Let's see. What do I want to put on the quiz on Thursday? There's going to be a proof, but again, and I'm writing this in chat again, that's going to be the, so the statements are given and you have to fill in the reasons. So there's going to be definitely one of those. And then I started putting stuff together. The other thing I want to test is contrapositive and converse. This is in 1.2. It feels like 5 million years since we've talked about it, but they are in 1.2. It's in the beginning of no, I'm lying. It's in 1.1? It's in 1.1. All the way back in 1.1. No wonder it feels like 5 million years ago. Back in 1.1, we talked about the contrapositive and the converse. You are going to want to know what those words mean and what they mean. If I ask you to say the contrapositive of a statement, can you do it? So those two ideas, there's going to be one proof where you have to fill out the statements, and I'm going to ask you a couple questions of, here's a statement, write the contrapositive, write the converse, stuff like that. So those will be kind of the two topics that you have on your quiz on Thursday. That's in the chat if you need it. These notes will be on Blackboard as always. The partial recording that I got will be up. I might go back and try to record the first bit that I missed later today because that was completely my fault. But those will all be up when I can get them up. Oh, your quiz that you just took the other day, I have them graded. They just haven't gotten into Blackboard yet. So those will also be in by the end of the day. And I will post the answers to the first quiz by the end of the day as well. So all that stuff. You can leave whenever you want because technically I'm 2 minutes over. But all that stuff will be up on Blackboard by the end of today. If you have some questions, feel free to stick around. Otherwise, have a great day. See you on Thursday. Yeah, I'm going to stop the recording now.